Good morning. Here, already I have taken two classes on distributed load from the chapter of statics, or actually, the name of the chapter is distributed load or parallel forces. Okay, that is the name of the chapter. Here, we are taking the most general case. Most general case means what? Say the distributed load is totally arbitrary. It is not like the shape of a rectangle, it is not like the shape of a triangle. It may be anything. It may be a circular arc, it may be elliptical, it may be parabolical, it may be anything. Okay. Again, the same case. One horizontal beam I am taking here, horizontal, okay, this one. Two simple supports are there at the two ends. Two simple supports are there. And the distribution is totally arbitrary. Okay, totally arbitrary distribution is there. Now, for such problems, if you can solve this problem, then you can solve any problem on distributed load. Okay, so this is totally arbitrary. So, what should be the approach to solve such problems? That is the question here. Say, along the length of the beam, this end is A, this end is B. So, reaction here will be denoted by RA, reaction here will be denoted by RB. This is the distributed load, and along the length of the beam, say, this along the length of the beam is x-axis, right? Since the distribution is arbitrary, so we can say that weight, that is the load, okay, weight, that is the load here, or force, downward force, that weight is function of x. Weight is arbitrary. That means along the x-axis weight changes. Along the x-axis weight changes. So we can say that weight is a function of x. So how we should write here this one? Small w within bracket x. Small w within bracket small w. Then start the bracket x, then close the bracket. That way. Wx means weight is a function of x. This is the meaning of this. Wx. That is the weight at any location x. That is the weight at any location x. So first, from the end A, this is the end, means here there is the origin of the x-axis. Location at this point is x is equal to 0. Here, somewhere here, okay? Location of x is 0 here. So at a distance x, somewhere here, at a distance x, you draw the vertical line. That vertical line will denote the weight there. Okay. Suppose that is equal to Wx. At a location x, weight is Wx. Or only W. That way also you can write. Only W. At a location x, weight is W. Then at delta x distance apart, delta x, which is very small, delta x is used, delta, this symbol is used only for small quantities. So at a distance delta x apart in this direction, okay, you draw another vertical line, so that length of the line will denote weight at the location x plus delta x. Now location, there is a change in location, okay. Here at a location x plus delta x, weight is suppose W plus delta W. Due to change in the length delta x, there is a change in weight delta w. So two vertical lines I am taking here, w and then w plus delta w, location x and location x plus delta x. Then what is the change in weight? It is w plus delta w minus w. W plus delta w minus w. And what is the change in location? X plus delta x minus x. So for what is the denominator here? X plus delta x minus x means delta x. And what is the numerator? It is w plus delta w minus w, that is delta w. So ratio is delta w by delta x. So we can say that for the distance delta x at this location, for the distance delta x, weight is how much? It is delta w. Right. Now you mathematically make delta x tend to 0. Means you take the limit. When delta x tend to 0, this ratio will become, what was the ratio? Delta w by delta x. That ratio will become dw dx, means dw by dx. Right? dw by dx. So that is what? That is weight per unit length. So dw dx is nothing but intensity of load at the location x. dw dx is intensity of load at the location x. So this way you have to approach to solve the given problem for any arbitrary load. At any location you take the intensity of load, then according to the length you multiply that length with intensity of load and then integrate. So you will get the total load that way. You will get what? Total load, that way you will get. Okay, suppose for this given problem, I want to calculate the total weight from the location x is equal to x1 to x is equal to x2, where x1 and x2 are final values. x2 minus x1 is say x2 is greater than x1, and x2 minus x1 is a finite value. This is not infinitesimal small value. Okay, this is a final value, x2 minus x1. So how you will calculate the weight for that span, x2 minus x1? Simply you write integration, then write that intensity of load dw dx. Then for an infinitesimally small distance dx, what will be the weight? It will be dw dx multiplied by delta x. Delta x. Right? dw dx multiplied by delta x. And when you are performing integration, this delta x will become dx. Now, in your given problem, w will be known in terms of x. W will be known in terms of x, means dw dx will be known. dw dx will be known in terms of x. So dw dx, that is a function of x, right, multiplied by dx. So this is the expression of which you have to take the integration. From the limit x is equal to x1 to x is equal to x2. Means lower limit will be integration sign, lower limit will be x is equal to x1, upper limit will be x is equal to x2. So this is the technique to calculate the total weight. Next, for the given problem, we know that if the total weight for the entire span is known, then for such problem RA plus RB will be equal to total weight. RA plus RB will be equal to total weight. Then one more equation is required to solve the given problem. You know this thing, and that thing you will get by using the principle. Since this is the problem on statics, so algebraic summation of the moments will be 0. Okay, here in this problem there are 3 forces. In the given problem maybe number of forces may be more than 3. Here 3 forces are there, RA and RB upward and the total weight downward. So total weight is now known. You have performed the integration and that way you have got the total weight, right? Now, whenever you will approach to calculate the algebraic summation of the moments, location of RA and RB are known. At location x is equal to 0, RA is there, and say length of the beam is L. Then at location x is equal to x, at the end, at location B, x is equal to L. So these locations are not known, so you can easily calculate the moment about any chosen point. The point is your choice. Okay. But still we do not know the location of the center of gravity of the distributed load. So that thing also you have to calculate. Location along the x-axis. So say along the x-axis the location is x bar, x on top of that draw a horizontal line and that is called bar, x bar. So x bar is equal to what? You know this thing? X bar is equal to sigma wx by sigma w. When you are taking algebraic summation of small weights, so in that case that sigma sign is used. X bar is equal to, from the chapter of centroid, you will get that formula, centroid and center of gravity. X bar is equal to sigma wx by sigma w. And in case of integration, that will be equal to integration of w dx what will be the integration? Integration of w dx, that is wrong. In the numerator, integration of x dw will be there. Integration of x dw divided by integration of dw. Integration of dw is nothing but the total weight. Okay, and in the numerator there will be integration of x dw. What is the meaning of that x dw? X dw is meaning of that thing is at the location x, weight is dw. And the product of x and dw is moment of the weight about the origin. X is measured from the origin. Location x is measured from the origin. So the product x dw which appears in the numerator, the meaning of that thing is the weight is nothing but a force. So moment of that weight about the origin. So in the numerator there will be integration of x dw, in the denominator there will be integration of dw. So this is what? This is nothing but x bar. So what should be the algebraic summation of the moments? It will be, if you are taking origin, means the location A as the moment center, then RA into 0 minus x bar into total weight of the distributed load. X bar is the centroid. Okay, x bar into total weight or center of gravity is here. Okay, and plus RB into L, that is 0. So in this equation RA will disappear because RA into 0 is there. Only RB is there. Then RB is equal to what? RB is equal to x bar into total weight divided by L. RB is equal to x bar into total weight divided by L. Now RB is known and one equation is already in your hand, that is RA plus RB is equal to total weight. From there you can calculate RA. So this is the way to approach to solve such problems on distributed load. This was just an example, okay? For the problems of distributed loads, concentrated loads or forces may also be there, okay? Anyway, this is the end of this lecture. Thank you. If you have any queries, you can write in the comment box. Okay. Thank you.